Greetings, fellow learners. Now, before we get into this wonderful world of the Perceptron, I have a thought-provoking question for you. How do you learn new things in general? Now, for me, that would involve making something a habit, and this instills the idea of repetition. So, for example, I have been doing yoga and meditation every day for over a year now, and my body and mind have learned about the flexibility and strength provided through this repetition. Now, in this video, we're also going to see how repetition can be linked to learning. So, passing this question over to you, how do you learn new things? Please comment your thoughts down below, and I would love to hear them. Now, this video is going to be divided into three passes where we're going to go through the biological process of what neurons are and learning, and then see how this influenced some of the big ideas for the perceptron, conceptual, and computational model. And we'll also show a demo. So it's going to be fun. Let's get to it. This here is a biological neuron, where we have dendrites, the cell body or the soma, we have the axon terminals, and a fatty substance that surrounds the axon known as myelin. Now, this neuron is connected to thousands of other neurons via their axon terminals. And the points of contact between their axon terminals of the previous neuron and the dendrites of this neuron is known as the synapse. And if we do like a little magnification here, we can see that these little dots over here are chemical messengers known as neurotransmitters. And these will send a chemical signal from one neuron to the next. And this will potentially increase the potential for every single dendrite if the potential or the membrane potential of the overall neuron becomes high enough over a certain threshold, then it will create an electrical signal, which is known as an action potential. And this is how signals can be propagated from one neuron to the next biologically. This signal processing is a complex process. And so we have a neurologist who is Warren McCulloch, and then a logician, Walter Pitts, come up with the artificial neuron in 1943. So the artificial neuron is a computation model. And what that means is, well, a model is a simplified representation of something that's more complex. And then a computation model means that it's going to be broken down into a set of computations or calculations. In this case, the model is of that of the biological neuron. So we take the complex signal processing of a biological neuron, and what they've done is broken it down into a sequence of simple steps that require computation. And they did this in order to understand the intelligence capability of the said biological neuron. And so what we have is this now McCulloch-Pitts artificial neuron created in the 1940s, where we have inputs, weights, and outputs. The inputs can be considered the inputs from different neurons due to like the neurotransmitter chemical signals. The weights are then different potentials that are caused by these individual dendrites. And you can consider this big circle over here to be the cell body. And then what we can do is we can compute a membrane potential, which is the sum of all of the individual weight potentials here. We'll call that M. And if this is greater than some threshold, T, it generates an action potential and the neuron fires. That's O is equal to 1. But if it is not greater than this threshold, then their neuron does not fire. And so we have now created a computation model of a very complex biological process. So a pro of this is that, well, the artificial neuron can function as a logic gate and do propositional logic. And what I mean by that is, let's say, we want to do an AND gate. We can fix a threshold as 2, set the weights to be like 1 and 1 for 2 inputs. And we can input 0 and 0 with the weights and threshold, do some calculation, and then you can get 0. Similarly, 0 and 1, you can get 0. 1 and 0, you get 0. And then 1 and 1, you get 1. So we can use this neuron alone to function as an AND gate. Similarly, we can do the same to make it function as an OR gate. We just need to reset the threshold and the weights, and then you can see that we can actually make computations such that it becomes an OR gate. Now we can also do the same as a NOT gate as well, where you fix a threshold 0, the weight is only going to be -1, so it'll take an input and then invert that input, whether it's 0 to 1 or 1 to 0. And we can even create a network of such neurons in order to create, more complex logical functions like XOR, where each of these is going to be a McCulloch-Pitts artificial neuron. And so this is our neural network here. So that's great, but the con here is that there's really no learning procedure happening. We need to fix the weights and the thresholds explicitly on our own when we're manually configuring this. And this is not how the brain works. It's an oversimplified representation. So for this neuron, how does this exactly learn? Well, we have Donald Hebb, who is a psychologist who came onto the scene in the 1940s, who stated that neurons that fire together wire together. And this is kind of the summarization of Hebbian learning that he proposed. Now, I'm going to describe a very simplified representation of what this looks like in action. So let's say that we have a very simple network of 3 neurons, and I'm going to illustrate something known as eye blink conditioning to illustrate a simplified form of learning. So one of the neurons here is a somatosensory neuron for detecting stimulus. Let's say in this case, it's going to be in the eyes. We have an auditory neuron to detect any kind of auditory stimulus. And then we have a neuron that's responsible for the motor skill of blinking, the action of blinking. Now, this by nature, the synapse over here is going to be strong, which means that whenever, let's say something enters your eye or your eye is stimulated, you are likely to blink. And so, hence, this synapse is strong. And similarly here, from an auditory neuron, if you hear something, you're not really likely to blink, and hence this connection or synapse is going to be weak. So what that means is, let's say there's a puff of air that enters your eyes, it's going to trigger your somatosensory neuron here and cause it to fire. Now, this is then due to the strong synapse. It's going to have a large number of neurotransmitters that are emitted over here. That's going to create an action potential and cause this neuron over here to fire. And hence, whenever there's a puff of air that enters your eye, you are likely to blink. Now, let's say now in a second case, you just hear the sound of some buzzing in your ear. Now, this is going to go to your auditory neuron. Now, your auditory neuron is going to fire. But because of the weak synaptic connection between the auditory neuron and the neuron responsible for blinking, there's not going to be a high enough potential generated in order to make this neuron for blinking fire. And so when you hear the sound of a buzz, you don't really blink, which makes sense. Now let's hear the third case, where you get a puff of air and a sound of a buzz at the same time. This causes their respective neurons to both fire. And now, because we have this visual neuron that's firing, it's going to cause the neuron responsible for blinking to also fire. And what you now notice here is because, byproduct of this, you will have an auditory neuron fire and this neuron for blink fire at the same time. They are firing together, and this causes a strengthening of the synaptic connection between them. And so, if we repeat this process of getting a puff of air and a buzzing sound, causing the neurons to fire, it's going to continue to strengthen the synaptic connection. And this, after repetition, will come to a point where when you just hear the sound of a buzz, it's going to cause the auditory neuron to fire. And because now this is a much stronger synapse, there's going to be more neurotransmitters that are able to go from the axon terminals of this first neuron to the dendrites of the second neuron. This can cause a rise in potential overall of this entire dendrite, and this can cause the action potential to be generated, and hence the neuron responsible for blink is going to fire too. Now, this action of like hearing a buzz and then blinking was not something that was there before. And hence, we say that some learning has happened at this very fundamental 3-neuron level. And so this is kind of the big idea that's being proposed with Hebbian learning. Neurons that fire together, wire together. So with McCulloch and Pitts in 1943, they created a simplified representation of the complex neurological process through calculations or computations with the artificial neuron. Now, Donald Hebb in 1949 proposed Hebbian learning, which demonstrates the link between neurophysiology, that is like synapses and neurons, with psychology, which is learning. And so summarizes neurons that fire together, wire together. Now, taking advantage of these concepts and also some other research at the time, you have Frank Rosenblat in 1958 create the Perceptron. This is a computation model of a biological neural network with the ability to learn from feedback. So, just like the artificial neuron, it is a computation model of a complex process. In this case, it's like a neurological process. But like Hebbian learning, it has some ability to now learn. And we're going to take a look at some higher level details about this perceptron in the next pass. Quiz time. Have you been paying attention? Let's quiz you to find out. According to Hebbian learning, learning is A, information stored as a coded representation in the brain. B, it's a property of the nervous system with information stored in the axon. C, it is a property of the nervous system with information stored in the synapse. Or D, none of the above. Note that multiple options here may be correct, and I'll give you a few seconds to answer this question. The correct answers are C. Now, can you tell me why? Give your reasoning in the comments below, and let's have a discussion. And if you think I do deserve it, please do consider giving this video a like, because it will help me out a lot. Now that's going to do it for quiz 1 and pass 1 of this explanation, but keep paying attention because I will be back to quiz you. Alright, so in this pass, let's take a look at some high-level details about the perceptron. This is a screenshot directly from Frank Rosenblat's Perceptron paper back in the 1950s, where we have this simple architecture of a visual perceptron. In this case, it's a perceptron of simply the visual system. Like this, you can have a perceptron for like auditory information and so much more. So let's say we have a retina over here. Now, this is going to consist of photoreceptors. These are cones and rods which can detect color, brightness, luminosity of objects that it perceives. Then these are then connected via localized connections to neurons in this projection area A1. And when we say localized connections, it means that specific cones and rods here are going to be connected to very specific neurons over here in this region. Now, the neurons here are then going to be randomly connected to other neurons in this association area A2. And these are also going to be randomly connected to other neuron clusters in these response regions. And we can kind of say that these responses are essentially clusters of neurons that are responsible for some high-level decision-making. And what we mean by that is like R1 could represent like, this object detected a tree, or this cluster of neurons R2 can determine whether we are detecting or perceiving a chair, and so on. So let's take an example here. So let's say that there is like this object over here. It's a tree, but it's an object right now. Now this is going to be perceived by the retina. So light enters the eyes and hits the photoreceptors, such as the rods and the cones. Then specific photoreceptors are now connected to specific neurons here, and these specific neurons will fire, right? And the specific neurons here will actually contain some low-level information. And this low-level information could be like the color of a single branch or a color of a single leaf. This is because they are directly connected to individual receptors that provide very raw, low-level information. Now, these neurons, through the random connections, are now going to be mapped to the A2 neurons. And these A2 neurons are going to have slightly higher level bits of information that are collected here, and these neurons are going to fire. And this could example be like the contour of branches with their leaves. So this is because, a single neuron in this A2 region could be connected to like a neuron in A1 that recognizes a single leaf, and then another neuron that recognizes a single branch, and kind of you can think of combining those pieces of information together to get the information here in A2. And we can also have multiple association areas here in multiple layers to get higher and higher levels of information. And then eventually, this A2 neuron or A2 neurons are going to be randomly mapped to the response cluster of neurons here. And one of these is going to fire. And in this case, let's say it's R1 that fires. Now, once R1 fires, the excitatory feedback from R1 will strengthen the synaptic connections of neurons that caused R1 to fire. So because R1 fired, all of the neurons that fired before this are now going to have very strengthened synaptic connections. Now, this is what happens in a biological case. This is actually what happens in human beings. But what the perceptron is kind of now doing is it is going to do the inverse of this, where instead of excitatory feedback strengthening synaptic connections, we will have inhibitory feedback coming from all of these other responses in order to weaken synaptic connections that didn't fire. Why do we do this? Mostly because of computational purposes. And we will see this actually in like the perceptron algorithm in the future past. So now what happens is, let's say we see another tree again. This is now going to enter the photoreceptors of our retina, and when a tree is seen again, the same assembly of neurons is likely to fire again, firing R1 in the process. So when you see a tree again, it's now easier to recognize because the same neural pathway connection is going to fire, and hence elicit the same response. It's a stronger response. And so the photoperceptron has learned to recognize the tree. And this is kind of the high-level intuition of the photoperceptron. And in the next pass, we're going to see a little bit more details about the algorithmic learning process. Quiz time! It's that time of video again. Have you been paying attention? Let's quiz you to find out. Which of the following, according to this diagram, is true? A1 will have neurons that capture low-level information, that is raw signals. B, A3 will have neurons that capture high-level information, that is recognition of an object as a whole. C, R1 does not provide any feedback. Or D, if R1 fires, the connections that caused R1 to fire strengthen. Note that multiple options here may be correct, and I'll give you a few seconds to answer this question. The correct options here are A, B, and D. But can you tell me why? Give your reasons down in the comments below and let's have a discussion. Now that's going to do it for quiz 2 and pass 2 of this explanation, but keep paying attention because I will be back to quiz you. In this pass, we're going to look at the algorithmic process for learning in a perceptron. So first we have our artificial neuron here. This is a computation model of a biological neuron. Model, simplified representation. Computation model, the simplified representation of the biological process is going to be broken down in 2 steps that require just calculations and computations. So specifically here, we can consider the inputs as inputs to the dendrites. Now these weights are going to be individual potentials associated with each dendrite due to previous connections. This could trigger now an action potential where we calculate the current membrane potential M, and it fires if it's greater than some threshold potential, or it doesn't fire if it's not. And so you can see how this is the computation model because we broke it down into a set of calculations or computations. Now, this is the architecture of the perceptron, where we have this is the equivalent of the sensory layer. Then we have the association layers, and then we have the response layer of neurons. And instead of localized connections or random connections that we saw in the original paper, we have more full connections to keep simplicity here. Now, let's say that there is some signal that enters the eye. Now, this is then going to propagate in the network where some neurons might fire and some might not. And this is going to be the response where, one of these neurons can determine if it's a tree, and the other is if it is a chair, right? So this becomes a computation model of biological learning and recognition via some visual inputs. So this is kind of our photoperceptron right here. So what is the computation that's actually done in this case? So let's say that we have like a data set where the input is going to be like 2 values right here, and the output is correspondingly going to be a tree. And we have several examples of this. And it's important to note that while the original perceptron made these inputs as 0s and 1s, we can actually generalize this to be, real value numbers too. So here's the algorithm where we will loop forever. And in this loop, for every input and label pair in the data set, we want to pass it into the perceptron in order to generate a response. And if this response is incorrect, that is, if the response is not the label, we will make updates to the weights in this way. So that is, we will say W is equal to the weight vector plus error times the input vector, right? And this error, it can be either like 1 or -1. Depending on whether we got it on one side of the decision boundary or the other side of the boundary. And like this, we will loop through every example in the data set. And only if every single example is correctly identified in the data set, it's only then that we terminate the process. Otherwise, we will keep looping forever. And you can see here that we mentioned before that in the computation model for this perceptron, we're using inhibitory feedback, where we are making updates to the weights in the case of error correction. And we're not just strengthening synaptic connections due to excitatory feedback. And this is for like the computation purpose you see here. Now I'm going to show a demo of perceptron learning right here. And I'll give a link to this little demo down in the description below, because it's not mine. Essentially, we have like a desired outcome, that is the label, which we call as D. We can then calculate the prediction, which is O, determine the error by subtracting the 2, and that's going to be our E vector, or error vector. And if we got it correct, we do nothing. But if E is not 0, that is either +1 or -1, then we are going to update the weight vector. Let's say that now we are going to put a point, let's say right over here. So I put like a red point over here. Let's say the desired feature vector is 1. We then now calculate the outcome. It's going to be 0. We got it wrong, and hence we need to update the weight vector. So the original weight vector was at -6 and +8, but then we will add EX in order to get this new weight vector over here. So if I put like another point over here, you can see that, well, is this wrong? It's going to compute that, the actual is 1. The desired is 1, so there's no error, and because there's no error, we do nothing. And we can do that for any number of points that we put here. There is no change in the weight vector. And so the linear decision boundary also does not change. But the moment I'm going to create a new point over here, which is wrong, it's going to be this green point. Now you can see that that green point is going to be incorrect. Now the weight vector, it's going to be subtracting that input vector, so the arrow goes the other way. It is then, in order to get like -x, and you add that -x to the weight vector, and that's now going to be the new weight vector. And when you get a new weight vector, you can see that the decision boundary is now going to change in itself. But in doing so, you can see that there still are points even now, this now newly misclassified point over here. But, we can still do some, add new data points here. I added a green data point, which should be correct, so there should be nothing done. But now let's add a point where it will be incorrect. So let's say we add a red data point over here, right? So that's now, we have a new X over there. You can see that we need to now add that vector to the current W. And so the weight vector is updated, and hence the decision boundary is updated. And you can see at this point of time, you can see that we have actually linearly separated all of our inputs, which is great. But in practice, this is just one step, and we can continue to do this again and again, continue iterating over the data set, which is great. So I hope this visual representation and animation kind of helps understand exactly like how these vectors updates are actually happening. And I'll link this down in the description. Now, a pro here is that we have a learning procedure. It's great. And this learning procedure will always find a linear solution that is a linear decision boundary if it exists within a finite number of steps. But the con here is that the learning procedure can be computationally expensive for large data sets. It's a long process. And the data must be linearly separable in order to converge to a solution. Because if it's not linearly separable, you can imagine that the perceptron algorithm will loop forever. Quiz time! Ooh, this is going to be a fun one. How many iterations will the perceptron take to converge to a solution? A, 1 iteration. B, under 10 iterations. C, over 100 iterations. Or D, the perceptron will not converge. I'll give you a few seconds to answer this question. Now, the correct option is D, but can you tell me why? Give your reasoning in the comments below and let's have a discussion. And if you think I do deserve it, please do consider giving this video a like because it will help me out a lot. Now, that's going to do it for quiz time and pass 3 of this explanation, but before we go, let's generate a summary. In this video, we introduced the biological process as well as the computation model for the artificial neuron. We also introduced, in the 1940s, the idea of Hebbian learning here, where that neurons that fire together wire together, and introduced this through an example of eye blink conditioning. And using these ideas, we had Frank Rosenblat create the Perceptron, which was a computation model of a biological neural network with the ability to learn from feedback. We also took a look at a high-level diagram of a photoperceptron where looking at an object repeatedly helps these neurons fire more easily, kind of seeing and instigating how the learning process can happen. We then took a high-level look at the architectural diagram of a perceptron and how it is designed in order to mimic, some parts of the visual system, though this can be expanded to other perceptrons. And we also took a look at this inhibitory feedback mechanism of how the perceptron actually learns. So this is its learning algorithm where it'll learn through an error correction update instead of learning through excitatory feedback. And with the demo, we show that this could actually be an effective learning procedure, especially if there exists linearly separable data, but it can lead to issues where the data sets are large because this becomes computationally inefficient, and also if the data is not linearly separable, as it could potentially loop forever. So that's all that I have for you today, and I hope this helps solidify a better understanding of the perceptron and why potentially we would need some more impressive learning strategies, including like backpropagation, which will come at a later place that's more computationally efficient than this strategy. But I hope you learned something today. Thank you all so much for watching. If you want to continue your journey through AI, click on this video right here. Thank you all so much, and I will see you in the next one. Bye-bye.